Microsoft Fabric OneLake Deep Dive, the unified data lake redefining enterprise analytics. Hello and welcome. Today we are taking a deep dive into Microsoft Fabric OneLake, the unified logical data lake at the center of Microsoft Fabric. OneLake is designed to give an organization one place to store, govern, connect, and analyze data across teams. It comes automatically with every Fabric tenant, so there is no separate storage account to provision just to begin using it. The big idea is simple: one logical lake for the whole organization, one copy of data where possible, and multiple analytics engines working on that same data. This matters because most enterprises are trying to reduce data duplication, simplify governance, and make analytics faster without rebuilding every pipeline from scratch. The easiest way to understand OneLake is to think of it as OneDrive for data. Just as OneDrive gives users a familiar place to store and collaborate on documents, OneLake gives the enterprise a common place to organize analytics data. Before this model, many organizations created separate data lakes for separate business groups, which often produced duplicated data, duplicated security rules, and duplicated operational work. OneLake changes that by making the Fabric tenant the top-level data boundary, and by organizing collaboration through workspaces. You cannot create multiple OneLakes inside the same tenant, and you can't delete OneLake from the tenant. That design makes OneLake feel less like another storage product and more like the default data foundation for Fabric. OneLake's organizational model starts with a Fabric tenant, then moves into workspaces, and then into Fabric items. The tenant is where broad governance, compliance, and security policies apply across the organization. Workspaces allow teams, departments, and data domains to manage ownership, access, and regional capacity boundaries. Inside workspaces, users create Fabric items such as lakehouses, warehouses, KQL databases, mirrored databases, semantic models, notebooks, pipelines, and other workloads. Those items store or reference data through OneLake while still giving different personas their own experience. This lets data engineering, data science, business intelligence, real-time analytics, and application teams collaborate on a shared data foundation. Under the covers, OneLake is built on Azure Data Lake Storage Gen 2 concepts and supports both structured and unstructured data. Fabric stores tabular data in Open Delta Parquet format by default, which allows the same data to be used across multiple engines. A data engineer can write data with Spark, a SQL developer can work through SQL experiences, and a Power BI user can analyze through Direct Lake without copying data into a separate import model. This is one of the strongest architectural points in OneLake. Storage is separated from the engine experience. The data can stay in one logical location while different compute engines read and process it. That reduces unnecessary movement and helps teams avoid engine lock-in. OneLake exposes data through familiar ADLS Gen 2 and Blob-compatible APIs, SDKs, and endpoints. This means existing tools can often work with OneLake with minimal changes rather than redesigning the application. A workspace behaves like a container, and a Fabric item behaves like a folder path inside that container. OneLake paths can use readable workspace and item names or stable GUIDs when names might change or contain special characters. OneLake uses a unified tenant-level namespace exposed through standardized endpoints rather than traditional storage account names. However, because OneLake is a managed SaaS service, tasks like permission management, workspace administration, and item lifecycle management still belong in Fabric, not in raw storage APIs. A lakehouse is one of the most important ways users interact with OneLake. When a lakehouse is created, it provides two main storage areas: tables and files. The tables area is for structured analytical data, especially delta tables that Fabric engines can recognize and query. The files area is for raw, semi-structured, unstructured, or general purpose files in formats such as CSV, JSON, Parquet, text, images, and other data types. This separation is important because not every file is automatically a table. Good OneLake design starts with knowing which data belongs in files for landing and exploration and which data belongs in tables for governed analytical consumption. OneLake is strongly aligned with the medallion lakehouse architecture. In this pattern, bronze stores raw data, silver stores cleaned and enriched data, and gold stores curated business-ready data. The bronze layer preserves original source data so that teams can trace lineage and recover from transformation mistakes. The silver layer standardizes formats, removes duplicates, validates quality, and joins related data. The gold layer organizes trusted data for dashboards, semantic models, machine learning, operational analytics, and decision making. In Fabric, these layers can be implemented with lakehouses, warehouses, or a combination depending on the team's skills and workload needs. A practical medallion design in OneLake often starts with raw data arriving in the bronze layer as files, delta tables, or shortcuts to external data. If the source already lives in OneLake, ADLS Gen 2, Amazon S3, Google Cloud Storage, or another supported location, a shortcut can reduce unnecessary copying. The silver layer typically converts data into delta tables and applies consistent business rules, data types, naming conventions, and quality checks. The gold layer focuses on curated tables that are easier for business users and semantic models to consume. Separate these layers into different workspaces when stronger governance and clear ownership are needed. That separation also helps teams manage permissions, lifecycle, and operational responsibilities more cleanly. Delta Lake is the default table foundation for Fabric lakehouses because it adds reliability to file-based analytics. Delta tables use Parquet files plus transaction metadata, which supports asset behavior, schema management, time travel, audit history, batch workloads, and streaming workloads. This matters because raw Parquet files alone do not provide the same transactional guarantees. Fabric engines can write delta tables by default, and refined silver and gold layers usually benefit most from delta's reliability and performance features. V-order optimization can further improve read performance for Fabric compute engines such as Power BI, SQL, and Spark. The result is a lakehouse pattern that behaves more like a governed analytical platform than a folder of unmanaged files. OneLake shortcuts are a major part of the architecture because they allow data to appear in OneLake without physically moving it. A shortcut is a reference to a target location, and the shortcut appears like a folder in the lakehouse or another supported item. The target can be inside OneLake, in another Fabric item, in another workspace, or in external storage such as ADLS Gen 2, Azure Blob Storage, Amazon S3, S3 compatible storage, Google Cloud Storage, Dataverse, OneDrive, SharePoint, or on-premises storage through a gateway. This creates a unified view across domains and clouds. Instead of copying data from every source into every project, teams can reference the data where it already lives. That reduces duplication, latency, and storage sprawl. Shortcut placement matters because the tables and files areas behave differently. In the table section of a lakehouse, shortcuts are intended for structured table data and must point to supported table locations. If the target is valid Delta Parquet data and follows the expected structure, the lakehouse can recognize it as a table. In the Files section, shortcuts can point to many kinds of data and can be placed more flexibly within the folder hierarchy. Table discovery does not occur automatically in the same way within files. A good design uses tables when the data should be queryable as a table, and files when the data should remain general-purpose files or landing zone content. Shortcuts can be used across many Fabric and non-Fabric experiences. Spark Notebooks and Spark Jobs can read shortcuts as folders or query table shortcuts with Spark SQL. SQL Analytics endpoints can query supported table shortcuts through TSQL. In real-time intelligence, KQL database shortcuts can be queried by using the external underscore table function. Power BI semantic models can use table shortcuts through direct lake mode when the data and model support that pattern. Non-Fabric tools can also read shortcut data through OneLake APIs, depending on permissions and endpoint compatibility. This broad access is what makes shortcuts more than a convenience feature. They are a key part of OneLake's data virtualization strategy. OneLake supports several shortcut source types, each with its own authentication model and limitations. EDLS Gen 2 shortcuts use a delegated authorization model where the connection is configured with credentials such as organizational accounts, service principals, workspace identity, shared access signatures, or account keys. These shortcuts must point to supported DFS endpoints and follow specific path requirements. Amazon S3 shortcuts are generally read-only and rely on credentials such as access keys. Support for other sources like Google Cloud Storage also exists with some limitations. Dataverse shortcuts are read-only and integrate Fabric with Dynamics 365 and Power Platform data through Dataverse managed storage. OneDrive and SharePoint shortcuts are in preview and are useful for accessing business files, though they may be affected by throttling and authentication behavior. These differences are important because each shortcode type has distinct security models, write capabilities, performance characteristics, and operational considerations. On-premises and network-restricted shortcut scenarios extend OneLake beyond publicly accessible cloud storage. With the Fabric on-premises data gateway, teams can create shortcuts to supported data sources such as S3-compatible storage hosted inside private networks. The gateway acts as a connectivity bridge between OneLake and the storage endpoint. This is useful when data cannot be exposed through public endpoints due to firewall, VPC, or network restrictions. Before creating the shortcut, teams should verify that the gateway machine can access and read the target data using the required credentials. This makes OneLake applicable not only for cloud-native architectures, but also for hybrid enterprise data environments. Shortcut security depends on both the shortcut location and the target data source. To create a shortcut, a user needs write permission in the location where the shortcut is created and appropriate access to the target. When accessing data through a shortcut, both the permissions on the shortcut and the target system are evaluated. Internal OneLake shortcuts use identity pass-through, meaning the calling user's identity is checked against the target data. External shortcuts use delegated authorization, where a credential configured for the connection is used to access the external system. This distinction is critical because pass-through keeps source ownership intact, while delegated access shifts some control to the connection and downstream governance model. OneLake security introduces role-based access control directly at the data level for content stored in OneLake. Security roles can grant access to specific folders or tables, enabling data-level protection across supported Fabric experiences. The goal is to define access at the data layer and have it enforced across supported workloads and access paths. Write permissions can be granted through appropriate roles, allowing users to modify specific data without requiring broader workspace-level access. Fine-grained controls such as row-level and column-level security are typically enforced through compute engines like SQL or Power BI rather than directly in OneLake. Users who do not have the required data access permission will not be able to view protected data. Data-level security capabilities in OneLake are still evolving, and so teams should evaluate current limitations before relying on them for critical production scenarios. OneLake security is different from compute-level permissions. Compute permissions apply only through a specific engine, such as a SQL endpoint or a semantic model. OneLake security is intended to protect the data itself across engines and direct access paths. This distinction matters because a user might be blocked in one compute experience, but still reach raw files through another tool if data-level controls are not applied. In some cases, compute engines provide advanced security features that OneLake security may not yet cover. When teams rely on compute permissions, they should make sure users can only access data through the secure compute layer, not through alternate OneLake paths. There are important identity considerations when using OneLake security with SQL and semantic model scenarios. In some cases, user identity is used to enforce access based on the calling user, while in other scenarios, access is based on a delegated identity such as a service or item owner. The exact behavior depends on the Fabric workload and configuration. Changes in identity handling can affect how access is evaluated and how queries are executed, even though the underlying OneLake data remains unchanged. Some permission updates are not always immediate and may take time to propagate. In some cases, shortcut validation or changes to target locations can temporarily affect query execution. These details are important because security design must consider both access control and runtime behavior. OneLake supports integration with external or custom engines in controlled scenarios. In these cases, an approved identity such as a service principal or managed identity can be used to access data stored in OneLake. Access to data is governed by OneLake security and the permissions assigned to that identity. External engines can read data through supported APIs, but they are responsible for enforcing any additional access controls required by their execution model. This enables integration with other processing engines while maintaining alignment with OneLake security boundaries. However, organizations must ensure that external access is carefully managed and that engines accessing OneLake data do so in a secure and governed manner. OneLake includes encryption, networking, and audit capabilities that support enterprise governance. Data at rest is encrypted by default with Microsoft managed keys, and customer managed keys can add another layer of control for supported Fabric items. Data in transit uses secure protocols, with TLS 1.2 enforced and newer versions used when supported. Fabric traffic between Microsoft services uses the Microsoft Global Network, and private endpoints can be configured for secure connectivity scenarios. Admins can control whether applications outside Fabric can access OneLake data. Audit logs capture many OneLake operations that map to storage actions, such as creating or deleting files, though log coverage varies by operation type and workload. Customer managed keys give organizations more control over encryption at the workspace level. Fabric data stores are encrypted at rest by default, but customer managed keys allow organizations to use Azure Key Vault keys for supported Fabric items. This supports key rotation, access control, usage auditing, and compliance requirements where customers need more control over encryption keys. The model uses envelope encryption, where a key encryption key protects the data encryption key. If a key is revoked, access to encrypted data can be blocked within a defined period. This feature has item support limitations, so teams must plan workspace contents before enabling it. OneLake includes built-in data protection for accidental deletion and regional resilience. Soft delete retains deleted data for a limited period, typically 7 days, allowing recovery through supported Fabric experiences and interfaces. OneLake storage is built on Azure Managed Redundancy, using zone redundant storage where available and locally redundant storage in regions where zone redundancy is not supported. Disaster recovery is managed at the Fabric capacity level, where data can be replicated to a secondary Azure region based on standard region pairings. If a regional failover occurs, replication is asynchronous, so data not copied before the disruption may be lost. This means OneLake provides strong platform-level protection, but organizations still need to plan for retention, backup, and recovery based on their business requirements. OneLake access patterns include user-friendly tools as well as developer-focused APIs. The OneLake File Explorer for Windows lets users browse workspaces and Fabric items through a familiar File Explorer experience. Azure Storage Explorer can connect to OneLake endpoints to upload, download, move, and inspect files. Developers can use Python with Azure Storage Data Lake SDKs and Microsoft Entra Authentication. Applications can use Blob and ADLS APIs to write or read data, depending on the workload pattern. This range of access options helps OneLake serve both technical and non-technical users, but admins must control external access settings carefully. For data engineering integrations, OneLake works with Azure Databricks, Azure Synapse Analytics, Azure HD Insight, and other ADLS-compatible engines. Databricks can read and update Delta tables in OneLake when the workspace and identity configuration support the required access model. Synapse Spark can write Delta Parquet tables into OneLake through ABFS paths, and Synapse Serverless SQL can read Delta data with open row set patterns. Azure Storage Explorer is useful for operational browsing and file movement. These integrations help organizations reuse existing skills and tools instead of forcing every workflow into one Fabric-only interface. The practical design goal is to connect tools to OneLake without creating unnecessary copies. OneLake also supports application ingestion and open mirroring patterns through Blob and ADLS API. When shortcuts are not appropriate, such as with proprietary systems or custom extraction logic, applications can stream data into OneLake landing zones. Blob APIs are useful for streaming and parallel block uploads, especially when writing large Parquet files from applications. ADLS APIs are useful for hierarchical directory operations, such as renaming and deleting directories. Because OneLake is a managed SaaS service and does not support every Azure storage operation or behavior, developers should validate API compatibility, permissions, file writing patterns, and error handling before using these integrations in production. This makes API design and testing important for reliable production ingestion. Open mirroring adds a structured pattern for bringing data into Fabric from external or proprietary systems. Applications write data files and metadata into a landing zone, and Fabric processes that data into Delta tables. The metadata identifies keys for upserts and deletes, while data files follow a predictable naming sequence. This approach is useful when source systems cannot be connected through shortcuts or direct connectors. It allows teams to write data in open formats while letting Fabric handle downstream ingestion details. For robust implementations, developers should test partial writes, naming logic, metadata creation, cleanup behavior, and retry handling. PlotViews 2 can be used in supported scenarios to mount OneLake as a file system on Linux virtual machines. This is useful for applications that are easier to integrate through file paths rather than SDK calls. A virtual machine can write data into the files area of a Fabric lakehouse, and the data can then be used by Fabric analytics workloads. The setup requires a Linux VM, network access to OneLake endpoints, a Fabric workspace, and an identity such as a service principal with the correct permissions. Performance depends on factors such as network bandwidth, caching configuration, region proximity, and concurrency. Because this approach is not fully POSIX compliant, behaviors like concurrent writes, file locking, and atomic operations should be carefully evaluated before using it in production. OneLake supports Apache Iceberg interoperability through metadata virtualization, which is currently available as a preview capability with important limitations. In supported scenarios, Fabric can expose metadata for Delta tables in formats compatible with Iceberg-based tools, and Iceberg tables can be accessed in Fabric through shortcuts when they follow the expected structure and metadata layout. However, this does not represent full bidirectional compatibility, and Delta and Iceberg tables are not interchangeable formats within OneLake. Proper folder structure and metadata placement are required for Fabric to recognize Iceberg tables correctly. There are limitations related to data types, metadata handling, partition transforms, multiple metadata versions, regional constraints, private networking, and certain shortcut scenarios. This capability is evolving, but it highlights the broader industry direction toward interoperability between open table formats in modern lakehouse architectures. Shortcut transformations help convert file-based data into queryable Delta tables without building a traditional ETL pipeline. Structured transformations support homogeneous CSV, Parquet, and JSON files from supported OneLake shortcut sources. Fabric Spark compute copies and converts the source data into a managed Delta table and keeps it synchronized. The service periodically checks for changes to detect new or modified files, detect deletes, and process subfolders for new transformations when configured. This is useful for quickly turning landing zone files into tables for SQL, Spark, and Power BI. Limitations include schema consistency requirements, unsupported complex data types, nested folder restrictions, and limited write operations on transformation output. AI-powered shortcut transformations extend this concept to unstructured text files. In preview, Fabric can apply built-in AI transformations such as summarization, translation, sentiment analysis, PII detection, and named entity recognition. The output is written as a Delta table that can be queried in using analytics. A practical example is customer feedback stored as text files, where PI can be detected and redacted before analysis. The service periodically checks for changes and updates the output based on source data changes. Current limitations include text-only input, regional availability, nested folder restrictions, and preview behavior that may change before general availability. Microsoft Fabric includes a catalog experience that helps users find data across the organization. As organizations grow, the challenge is not only storing data, but helping people discover the right data without browsing every workspace manually. The catalog supports discovery across Fabric items and helps users understand what data exists, where it lives, and how it can be used. This is especially important in a distributed ownership model where departments manage their own workspaces. A good catalog strategy should include clear item names, descriptions, endorsement practices, sensitivity labels, and ownership metadata. Without strong discovery practices, even a unified data lake can become difficult to navigate. Lifecycle management is another important part of OneLake architecture. Shortcuts can be managed through the Fabric portal or through shortcut REST APIs that support iterations such as create, delete, get list, and bulk management. Workspace variables can be assigned to shortcut properties in preview, helping teams deploy solutions across development, testing, and production environments. This allows a shortcut in test to point to test storage, while the same logical solution in production points to production storage. Only string variables are supported for this feature in the documented preview. This matters because real enterprise lakehouses require structured deployment practices, not just interactive configuration. OneLake capacity and cost behavior must be understood before large-scale rollout. Storage is built based on data stored within OneLake, while data operations and processing are generally reflected through Fabric capacity consumption rather than traditional storage transaction billing. Disaster recovery can affect both storage and capacity usage because data is geo-replicated and additional operations may consume capacity. Security features such as row-level security are enforced by compute engines and can impact capacity depending on query execution patterns. Diagnostics events written to a destination lakehouse can also contribute to capacity usage, so monitoring through Fabric capacity metrics is an important part of operational governance. Performance optimization in OneLake is not only about choosing the right engine, file size, table maintenance, partitioning, clustering, and retention all affect query performance and cost. Large analytical platforms usually perform better with fewer larger files instead of many small files. Bronze layers may tolerate smaller files because ingestion patterns are raw and frequent, while silver and gold layers should be optimized for larger files and efficient query access. Partitioning can help when access patterns align with query filters, but over-partitioning can reduce performance. For refined layers, techniques such as clustering and table maintenance may be more effective than excessive partitioning, depending on the workload. Historical retention should also be part of the Delta table strategy. Delta tape keeps transaction history, which supports rollback, auditing, and time travel, but metadata and retained files grow over time. Organizations should define how long history must be kept based on business, compliance, and recovery needs. The vacuum command can remove unreferenced older data files once they are beyond the configured retention period. By default, Delta protects recent deleted files from being vacuumed too soon to maintain consistency. This is a practical example of balancing reliability, compliance, storage costs, and operational performance. There are also important limitations and design constraints to remember. OneLake managed folders protect Fabric item structure, so workspaces, items, and managed folders are not created or deleted through raw ADL's APIs. Some API operations, headers, and parameters are not supported because OneLake's permission and management model differs from traditional Azure storage. Some external tools may require updates if they depend on older storage endpoint patterns or unsupported behaviors. Shortcut names and paths have character restrictions, and shortcut nesting has limits. Table recognition can take time after shortcut creation depending on metadata validation and system processing. A successful OneLake rollout requires teams to understand these constraints before standardizing patterns. A strong OneLake operating model should define workspaces, domains, environments, naming standards, security roles, shortcut ownership, and table lifecycle practices. Teams should decide when to use shortcuts, when to transform files, when to mirror data, and when to physically ingest data into Delta tables. They should also document which identities own external connections and how those credentials are rotated. Security should be designed at the data layer first, then supplemented with compute-specific controls when needed. Monitoring should include capacity usage, storage growth, shortcut health, transformation status, and disaster recovery settings. Governance works best when it is built into the architecture from the start, not added after data sprawl begins. The most important takeaway is that OneLake is not just a storage layer. It is a unified data foundation for Microsoft Fabric that brings together open formats, common governance, multi-engine analytics, shortcuts, security, API access, transformations, and disaster recovery capabilities. It helps organizations reduce copies of data while still supporting distributed ownership across workspaces and domains. It gives engineers, analysts, administrators, and business users a shared platform without forcing everyone into the same tool. But OneLake still requires thoughtful architecture, especially around security, shortcut design, table optimization, cost, and lifecycle management. Thank you for taking the time to explore this topic, and I hope this deep dive helps you design better data platforms with Microsoft Fabric OneLake.